Assalamualaikum warahmatullahi wabarakatuh. Okay, we will look into this question. Okay, this question had been asked by one of your colleague. So question number 2 from the handout that had been given before. So a radiation detector in a laboratory records a reading of 10 counts per minute. So this is the reading detected by the detector without any radioactive substance. Okay, so this can be said as your background radiation. Okay, background radiation. So there are no radioactive samples in the lab. Carbon 14 has a half-life 5,700 years. So this is the half-life for carbon 14. So carbon 14, the half-life is equals to 5700 years. Years. There are atoms of carbon 14 in all living organisms. Okay, an archaeologist digs up some ancient wood. So he found an ancient wood. In the lab, a sample of this ancient wood gave a reading of 20 counts per minute. So when he brought this ancient wood into his lab, where we know that before in the lab there is background radiation of 10 counts per minute. So he brought this ancient wood, and what is the reading detected by the detector? It gives 20 counts per minute. Okay, 20 counts per minute. So we can put it n equals to 20 counts per minute. Okay, so this 20 counts per minute is actually the reading of ancient wood. Okay, this is actually the reading coming from ancient wood plus, okay, don't forget the background radiation. So how to get the actual reading produced by the ancient wood? So the n is actually ancient wood equals to 20 counts per minute minus 10 counts per minute. So we will get 10 counts per minute. So this is the actual reading coming from the ancient wood. So it gives 10 counts per minute of carbon 14. Okay, an equivalent sample of living wood. Okay, and then in this question it state that for the same living wood, okay, for the same wood, but it is a living wood. Okay, previously we have ancient wood. Okay, the one that had been dead before, and then if we have the same wood, but if it is a living wood, okay, it will give reading of 80 counts per minute. So n living woods, 80 counts per minute. And then this reading is the reading that we will get in our lab. It is 80 counts per minute. So the actual reading coming from the living wood should be 80 counts minus the background radiation. So you will get 70 counts per minute. Okay, per minute. So now we have two readings. The first one, after it deads a long time, which is 10 counts per minute, and the one before it died lah, which is 70. So when we want to investigate the age of the ancient sample, okay, we know that the time when the ancient wood is still living, the count should be 70. So we can say that the initial reading should be 770. And then the one after it is being brought by the archaeologists, where after a few years, okay, and then it become ancient wood. So the reading is The reading is n equals to 10. So you have initial reading, and then you have uh, the reading after a few years. Okay, after a few time being decayed. So from this information, we can show that, okay, we can try to calculate the age of the sample. Okay, we know that initial reading coming from the wound should be 70. Okay, should be 70. And then carbon-14 is one of the radioactive materials. So that means it will decay. And the decay process should follow the half-life of the radioactive substance. That means it will decay. We can predict the time if we look into the amount that being decayed into half. So from 70, first it will get into 35. Okay, 35. So this is for one half-life. One half-life. And then from 35, it will decay into half of 35. So if you calculate 35 divided by 2, you will get 17.5. Okay. So if you look here, the reading after a few years, okay, the one that we want to investigate the age of the wood is 10. So we try to get into 10. So 70.5, okay, we cannot divide into 10, okay, produce 10. But what we can do here is we try to divide this number 17.5, divide by 2, so we will get 8.75. Okay, 8.75. So that's mean we can find where is the time, okay, the zone when the reading should be equals to 10. So 10 is approximately here lah. Okay, this here just before 3 half-life, after 2 half-life. So here we have 1 half-life and then 2 half-life. Okay, and then if the reading become 8.75, we can see that it is 3 half-life. Okay, but it is not reached yet 3 half-life, maybe just beyond 2 half-life. Okay, but actually we can confirm that. Okay, here we can confirm that at least the age of the ancient wood must be larger than these 2 half-life. Okay, so 1 half-life is equals to 5700. Okay, 5700. So here we have 1, 2 half-life. So the total time ataupun the total age is equals to T equals to 2 half-life at least. Okay, at least the age of the ancient wood must be equals to 2 half-life. So we try to multiply this number 2 times 5700, and then we will get, okay, 2 times 5700 11400. Okay, so it follow what had been suggested here. Okay, it is 11 for 400. Yes, don't forget the unit. Okay, 11 400 400. Yes. Okay, of course it is more than 11 400, because if it is 11 400 years, that means the reading should be equals to 17.5. Okay, but the reading that we get is where is the value? 10. Okay, it is 10. So it is beyond more than 11 400, and it must be, if we try to calculate here, what is 3 half-life? Okay, 3 half-life. If it is 3 half-life, 3 times 5700, we will get 5700 times 3, okay, 7,100 years. Okay, so our age should be more than 11,400 years, but it cannot exceed 7,100 years. Okay, as you can see, it cannot. Okay, 10 here. Okay, this is 10, count rate of 10. It is not exceeding the value of a reading after 3 half-life. So that's mean the age cannot exceed 17,100 years. Okay, so at least here we can prove that we can suggest, okay, we can confirm that the age of the ancient wood, at least it must be 11,400. So you can get 4 marks for this question. And thank you for your question. That's all for this session. Okay, I will end this session, and thank you.